Hi everybody, my name is John Dagdalen. I'm a graduate student in the Pearson group, and I've been with the group and the materials project for a few years now. I'm going to be talking about the materials API. So this is our favorite way of getting data from the materials project database, along with some useful functionality. And so over the next hour and so, we're going to be talking about MAPI, also its documentation, which is a critical part of any software project that I think always deserves good attention on how to find the information that you need. We've already gone through getting API keys, but I'll briefly go over it again for anybody that maybe missed that section of the first session. We're going to talk about in depth how to use the MP rester to access our database and get the information you're looking for. And then we're going to be doing a hands-on example, a couple of them actually, on how to use data in a kind of materials informatics way to get new lenses on the materials landscape, and how to do materials discovery through the kind of classic funnel workflow that we talk about, even though funnels don't actually physically work that way. So the first section, getting an API key. So if you don't already have an API key, if there's any of you, just go to the materialsproject.org/dashboard. If you click this link in your notebook, it'll take you straight there. And then right in the center of it, there should be a little box that says Generate API Key. If you already have an API key and you've set it in the first session, don't click this button again, because it'll invalidate that old key. If you have done that, just copy the new key and then paste it in this line here, and then run this cell with Shift-Enter. How is the text size for the people in the back? Can you read the code cells fine here? Okay, cool. So the first thing that we're going to cover is the MAPI doc. So I wanted to start with the documentation, and then also in the middle maybe we'll reference it a couple times because it's that useful. So the MAPI doc is going to be kind of the key source of information when you're trying to figure out what's in the database and like how to find it. So off the top of my head, I usually don't know, like I work with the materials API a lot, right? And even I don't know specifically, 3 levels deep, what are the keys of the information I'm trying to get out of the database. So for example, if I want to get the name of a space group or the crystal, like if it's cubic or not, right? I may not know off the top of my head what I actually need to search on when I'm doing my queries to the database. So the MAPI doc is kind of the center of all information about this. So it's a GitHub repo, as you'll notice. And the structure of it is actually the same as the structure of the database. So if you go to materials here, you'll notice that there's materials and tasks. The other stuff is specific to examples in GitHub. So we go to materials. You'll see here that the folder structure of this GitHub repo actually mirrors the structure of our database and how you query it. So say I was interested in for example, the space group example I was talking about before. If I scroll down here, I see that there's a folder space group. So this is materials space group. And then now there's an example of a space group and what it would look like as a document in our database. And maybe I wanted the crystal system, like I mentioned before. So if you look at the top here, so it's MAPI-doc, materials, space group, crystal system, and then this is the end of the road. So it's just a string, trigonal. So in our queries, what we can do is we can basically use space group dot crystal system and query into that field of this array. So how many of you attended the MongoDB primer? And then how many people didn't attend that MongoDB primer? Have you used Mongo before? None of you? Okay. So I'll talk a little bit about how Mongo works when we get to that section. Okay. So we kind of covered this in the beginning, but the API is essentially a computer sitting somewhere in the cloud, and you can access it through the internet. One way you can do that is through your web browser with an HTTPS query. And so this is actually a GET request, so it's trying to get some data out of it. So if we look, what we find here is materials, MP24, 1234 VASP, and then we're giving it an API key. And the response that this gives is this dictionary, as we've now seen. And essentially, this dictionary is if you look at this space group dictionary you get here, this mirrors sort of the database entry that we just looked at in the MappyDoc. So you can see here that there's a symbol and a crystal system field in that document. Of course, we want to do things programmatically, so we can do this with Python, actually. So let's go ahead and let's do that same request that we just did for the like in the HTTP request. Let's use the Python requests library. So I'm kind of going to show you a little bit behind the scenes of the MP Rester what's going on. So there's a library in Python called requests. So let's go ahead and import requests. So import requests. And then let's get response. So we need to do a get request. So that's requests.get. And then we're going to give it the endpoint that it's hitting, so the URL from the previous slide. So let me copy that. I'm going to go to the previous slide real quick and copy it. And I'm going to copy everything up until the question mark. And then and I'm going to just paste that in here. So you should do the same. And then we're going to put a comma at the end here and add another parameter. And this parameter is going to be a dictionary. So I'm going to use the curly brackets to make one. And the key of that dictionary is going to be API key, API underscore key in all caps. And then we put a colon. And then you should paste your API key here. Let me get mine real quick. So yours should be a little higher up in the notebook. So I'm going to have to change my API key after this since we're webcasting it. But for now, here we have it. And so let's just run this. So as you can see here, the cell ran. There were no errors. So let's just see what this said. We're going to print response.text. Not test, text with an X. So this response is an object, and it has this field text in it, an attribute. And then what we see here is the same thing that we got in the web browser before. That's what's returned. So now we have it in Python, though. So we can start doing things with this data. And if I look at this, it looks like a Python dictionary, right? So that's the kind of nice thing about JSON is that it mirrors this data structure that we work with a lot in Python. So this is kind of what's going on behind the scenes in the MP Rester is we've essentially written code to do all these kinds of requests on the different API endpoints that you might be interested in. So for example, get materials IDs, what it does is it queries the formula like type areas in the database documents, and it finds all the material IDs that match that query that you just did. So there's lots of code that use like the request library to do this. So you can kind of have an idea how you might, if you have a special workflow that you want to make that the Rester doesn't cover, you can use Python to just query our database directly and then consult the MappyDoc to get the data that you're interested in. A little bit later in this lesson, I'm also going to show you how to use the query method, which just lets you put straight Mongo-like syntax into a parameter for your query, and it'll just give you back the data you're interested in. But if you wanted to somehow do this in a programmatic way without using that query method, you can just hit the API directly with the URLs. With the URIs, they're called, actually, in Rest. So our Rester, the code connects the database, our code connects the MP database through REST requests. And Pymatgen's MP Rester is code that connects to our database that way. And it also has its own documentation. So let's go ahead and click this link to the MP Rester documentation. So as we notice, this is different than the MappyDoc. The MappyDoc is about the structure of the database. The Rester is about how the Rester functions. So now this is Python documentation. So you'll notice that here it's a class. So the MP Rester is going to be an object when we instantiate it. And objects can have properties associated with them, which is like single pieces of data that you get with a period and then the name of that variable afterwards. And they can have methods, which are functions that are associated with the class. So an API, the MP rester takes in an API key. It can also just take in another endpoint. So if you have a experimental, maybe like another version of the MP database, you took the MP database and then you augmented it somehow, and you have your own Mongo database, you can actually just put the endpoint of that and then have the same MP rester functionality on another database. So if you wanted to supply the endpoint. And then you can see here that it starts documenting the different functions here. So there's a function find structure. So you can actually, so there was a question earlier about how do you check if the materials project has a material in it easily if you have a structure. You can actually use this method of the rester and give it the file name of that structure. So if you have a CIF file and you want to check if it's in the materials project, you can actually just put that file name in there and then find that structure. Substrates, band structure by material ID, which we used before. So there's lots of functions here. So if you ever are wondering like what do I need to put into this function to get the data I want out, or what is it going to give me, this is the documentation you consult for the rester specific stuff. So I'm going to go back to the notebook. And so we've already gone through this, but I'm going to skip ahead to past the with context manager stuff. So we already know how to create an instance of the MP rester. And as we did before, you can see that we had the plotting function, and we did an exercise where we got a band structure and then plotted it. So let's go ahead and do another exercise where we get the MP IDs for a formula or chemical system. So what I'd like to do is show you a couple ways that you can query for materials in the materials project, so that the MP IDs, based on maybe you wanted a specific chemical formula, or maybe you didn't know like the specific formula, but you wanted to know all the materials in a chemical system. So let's go ahead and let's do this for lithium iron phosphate, which is a neat battery cathode material, lithium ion battery material. So we've already done with MP rester as MPR. So let's do MPR dot get materials underscore IDs. And then what are we going to put here? Just the formula. So the formula is LiFePO4. And let's go ahead and, so I wrote a small function called shortlist just for the purposes of this demo slide. By the way, you don't have to run the Jupyter notebook in Rise mode or in the demo slide mode. You can just run it as a normal notebook. I highly recommend that. I'm just doing this so it's all visible easily. So I'm going to write shortlist, but anytime I write shortlist, just go ahead and write print. And it's going to be much longer, but I wanted just only 5 things to print. So I'm going to write shortlist. So this is just essentially a print function that's shorter. So the reason I got this error is I haven't actually run the code to import the MP rester. So from Pymatgen import MP rester. Let me quickly run the cell with shortlist in it. Sorry about this. So now you can see these are the results for lithium iron phosphate. So it tells you, my shortlist function will tell you it's the number of items and then how many total there were. So let's go ahead and let's try this for the chemical system, lithium, iron, phosphorus, oxygen. So this is going to give us every material that has, that's in that chemical system. So mpr.get materials IDs. And let's do li/fe/ or dash, not slash, I'm sorry, p-o. And I'm going to wrap this in a print statement. Now we can see there are 303 items, and 303 is also the area code of my hometown, so that's cool. And so we have a lot more structures in this system than just the lithium iron phosphate. Oh, you have a question? Sorry, go ahead. Okay, go ahead.
Why can you still look for the? Can you just go back to the slide? Yeah. You write Li in capital letter. How come that it's working?
Oh, I think there's probably some. I don't know specifically about the capitalization, but I suspect it's just lowercasing everything because the element names don't overlap. So when you have the dashes and it knows it's a chemical system, maybe it doesn't care. But it shouldn't change the number. Oh, interesting. Okay, maybe you're right. So it didn't actually parse that properly. So what happened is that it probably saw L capital I and said, that's some random thing. I'm not going to include that. So that's why we got only 303 items instead of 812, because it was looking at a reduced set. That's a good question. Did you have one? Same thing, or? Okay. Cool, thanks for catching that. So yeah, you do have to have the correct capitalization on your element names. Okay, so let's do an exercise so that this has a chance to sink in and stick. So imagine you want to get the structure of this multi-ferroic material, BiFeO3, and I have its MPID up here for you. And also, let's get some substrates for that. So say that we wanted to do some sort of growth of this material, and what would be an adequate material and surface to grow this material on that has the lowest elastic energy difference between a film on it. So there's two methods that you might want to use: mprester.getStructure by material ID, and also mprester get substrates. So you want a structure so that maybe you could view it with the crystal toolkit, and you want the substrates. So go ahead and one thing you can do is actually do the if you highlight a piece of code and then you hit Shift Tab on it. I'll zoom in here. You actually get a tooltip for it. And this actually is the documentation that I pointed you to earlier. These are the doc strings. So you can actually see what it gives you. So mprester. So my notebook got weirdly this is strange. Okay. Let me go back. Sorry about this, everybody. The example is, here we go. Okay. So if you've successfully got the structure and a list of possible substrates, go ahead and put a green sticky up. If you're unable to do this so far, or you have a question, you can ask me a question now, or you can put a red sticky up if it's something that one of our helpers can help you with. Okay, so we are going to first create the mprester. So with mprester as mpr. And let's get our structure first. So I'm going to create a variable named structure. Helpers, we have one person here. And what are we going to put here? We're going to use the mpr dot maybe get structure by material ID. And we're going to just pass in the MPID as a string. And now for the substrates, if we were unclear about what the substrate endpoint of the rester takes, we can consult the documentation, and you'll find that it says it just needs a material ID as the input, similar to get structure by material ID. So let's write substrates, because it returns a list, as we would see in the documentation. And we're going to do the same thing, mpr dot get substrates, and then the MPID. And let's go ahead and just view the structure. So let's view the structure file, I guess like parameters, not the viewer. So print structure. And then I'm going to also go ahead and print the substrates. Let's see what we get here. I'm not able to scroll, so I'll rerun the cell. So first we see we get the structure for it. And then I'm going to comment this cell out and then rerun so we can see the short list of substrates. And then you can see here that I actually just did a quick search on Google for the substrates you might use to grow it. And it looks like this, like a few of these are actually real substrates that people use to grow this material. So it's a pretty good tool. And so these are just a couple examples of the functions that you can use of the MP rester. Okay. Any questions? Yeah?
How can we select the good substrates?
Mm-hmm.
Just calculate the reaction energy or the absorption energy?
So it looks at the, so say that when you're running a substrate, it's going to be like epitaxial at those first few layers. And so what it does is it looks at the lattice mismatch between them and the elastic constants of the two materials and gives you an energy term associated with like forcing those two materials to conform to each other. And so it picks the ones with the lowest energy mismatch, or the lowest energy that it takes to create that.
It doesn't have anything to do with the elements, but just the structure?
I believe so, yeah. So at this point, you should be comfortable with finding the documentation on the rester and also on the MappyDoc, creating an instance of the rester and using its methods. So this next section is going to cover, where are we? We're going to be talking about the MP rester's query method. So this is where the real rubber hits the road with the MP rester. This is how we query on the database for any information we want based on any parameters that we want to specify. It uses MongoDB's query syntax, which you saw in the primer if you were here for that. If you weren't here for that, I recommend that you click this link to the query syntax that's in there and just kind of take a look at like the couple short examples that they're going to include there of just like basic queries. So if you're unfamiliar with Mongo, it's kind of basically you pass a dictionary in, and we're going to go over this. But this is probably the most frequently used method of the MP rester in my workflows. So generally, the way you call it, this is kind of strange how it formatted this here, but okay. So the general structure is that you do mprester.query, and you pass two arguments. One is criteria, and the other is properties. So criteria is the list of like filters you want to apply. I want things with 5 elements in them that don't contain lead. The properties are what data do you want out of the database. We enforce that you need to tell us what you want so that we don't just give you everything. So if you want the structure, you're going to write structure in there. So let's take a look and see how it works. So let's just try to calculate to get data for SiO2, and let's use the query method instead of the get materials IDs method that we used before. So I'm going to go ahead and just instantiate the MP rester itself so that I can start pulling up some of the auto completion. So mpr dot query. So if you're interested in just getting very simple queries done, like I want this materials formula or I want this chemical system, you can actually just write this as a string. So let's just write SiO2 here. So this is like our criteria. And now let's do the properties. So the properties actually has to be a list, so we're going to use square brackets. And we're going to just pass in the names of the properties that we're interested in. So let's say we wanted to get the material ID. And then let's go to the MappyDoc and pick a property that we're interested in. So I'm going to go to materials. So maybe something in here catches my eye, such as density. So if we get the density, we should just get the density of the material back. So it's going to be a string, and I'm going to write density. And then I'm going to print that. So as you can see here, what did we get back from the query method? It's a list of dictionaries. And the keys of these dictionaries are the properties that we asked for. So material ID, or the data that we asked for, material ID and density, material ID and density. So you can actually use also wildcard characters in your queries. So let's go ahead and let's get every ABO3, so every like perovskite type material in the materials project database. So how do we do this? So I'm going to do mpr.query. And I'm going to pass it a string. So wildcards are these stars. So if we do star, star, 03, and let's go ahead and get the material ID and maybe the formula, like maybe we want to know what the actual A and B are. So if we consult the MappyDoc, and I can just go to the search bar and type formula in this repository, you can see here that there are a few different like types of formulas that I could compute or get from the database. And if you scroll down a bit, you might find something called pretty formula. Anyway, so you can get the pretty formula, which is basically the kind of one that we're used to. Pretty underscore formula. And maybe I also want its material ID, material underscore ID. And this may give us a lot of results, so I'm going to also add my shortlist function, but you don't have to. And then I'm going to hit shift enter to run this cell. And you can see here that a little loading bar pops up. And so when you're requesting a lot of results from the materials project, it kind of, from the API, it'll chunk up, the MPRS will chunk up your requests and then run each of those separately so that you don't time out or like hammer the server with too much. So it's all handled for you. You don't need to worry about it. But if you see a loading bar, that's what's going on. And you can see here that we just got a bunch of perovskites. Any questions so far? All right. So now, there are 296 variants of SiO2 in our database, but how many SiXOY compounds are in the materials project? So I'd like you to use a query, and instead of querying for the formula, pass in a dictionary where chemsys, the key chemsys, and the value of that dictionary is going to be the chemical system for Si and O. And then tell me how many results there are in the database. Yeah? You got one result. So that may be because you searched the chemsys you searched maybe was the, did you use chemsys colon something, or did you just search with a string?
Just the string with the last part.
Yeah. So that might that might be why. So to do a query here, what we're going to do is have chemsys. So we're actually passing a dictionary this time, not a string. And then the value of this dictionary is going to be si-o. And then let's just print the length of this with len. Oh, I got 0 results. What's going on here? So
you can do it without the chemsys.
Oh yeah?
Yeah.
Yeah, I guess you can just print this here. But I wanted to show you guys the syntax we're going to be using soon. So if you look at the mappy doc, and we're going to search, we're going to just go to the home and search. You don't have to look in the documentation since I'm doing this. So I'm searching for chemsys. So it says a string of chemical system associated with the material gives you an example, and it says, note the element symbols must be in alphabetical order. So if you ever hit an error where you think something's not quite right, it's good to consult the mappy doc. And you can see here that this isn't the alphabetical order of this chemical system. So it's doing an exact match. When I use query with the brackets, it's doing an exact match on what I'm searching, not using any of the back-end stuff that we've programmed in. Because Mongo doesn't let you search on strings like we show here. It uses these dictionaries and it matches exactly when you're asking for that operator. So if I replace the order of ONSI, now I should get this result again. So I accidentally deleted my chemsys key, chemsys colon OSI, and now I get the same number. Mm-hmm. Yeah. So if you wanted to look in multiple chemsys, we're gonna go through that in just a second. But you're gonna use another operator. So right now the operator this is using is like match this exactly. But you can also use an operator for and. So if you wanted to combine queries, you say and this chemsys and this chemsys. So we're gonna do that in just a second. Yep.
Okay, so if I just like print that out instead of doing the length, I get a bunch that say there's nothing. Like there's no materials ID. So if I so
Interesting. Let's do this.
Materials ID and it said materials ID none.
Okay, so that might be because so if you give it a key that is it the misspelling in the key, Matt, or okay, yeah. So it's going to give you data for that field, and the documents don't actually have that field, so it's going to put none there for you instead of throwing an error. So that's a good that we caught that here, so that everybody's aware of that.
So how is this different from writing chemsys and without writing chemsys?
So when we just wrote the chemsys as a string and not a dictionary, that was getting taken in by our database, our API server code, and being processed, and then the query is being done. But when we use the dictionary method, there's no processing being done on that dictionary. It's just going straight to Mongo. So the syntax has to be proper Mongo syntax once you hit that. Like more specifically, proper Pymongo syntax, because there's a slightly different way that MongoDB regular syntax uses operator keys. Okay, so let's go ahead and do an in-depth example. So I love silicon dioxide. I wrote a paper on it, and it's a neat system. So let's go ahead and let's see what's the distribution of SiO2 compounds in the materials project database. So this might be an interesting example to do. And then we're going to plot a bar chart for it. So the first step is collect all entries in the materials project database with the formula, and then collect their crystal systems, and then plot a bar chart for it. So I'll leave this up. So since we're I guess we're doing okay on time. Yeah. So the plotting code is kind of not part of this lesson. So if you're less familiar with different plotting codes and you want to make a quick histogram, if you go to the main, I'm going to move away from the slide just for a second to show everybody. So if you go into the main directory where the notebook that we're using is, you can go to API use filled. And then the code for plotting is in there, and you can just copy that or just read it and understand what's going on. Because we might have to type it kind of fast, and I don't want to lose anybody. So don't worry about typing all the plotting code, because it's not necessarily important to the content that we're trying to learn here. Any questions before I go through the solution? Okay. So the first thing we want to do is import a plotting function. So let's do import matplotlib. And let's go ahead and just get the pyplot function of matplotlib. So import matplotlib.pyplot as plt. So it's a little shorter. And then I'm also going to do this little character %, and then write matplotlib inline so that it will produce the figure in the notebook. So there's a space in between those. And then I'm going to create the MP rester with MP rester equals MPR. So with MP, and I'm going to hit tab to autocomplete. So I typed MP and I hit tab and it just filled it in. This is a really nice skill with Jupyter that allows you to type things much faster. So I'm a big fan of that. As MPR. And then let's go ahead and get our query for the SiO2 compounds. So mpr.query. Query. And then the first category, we know it's just going to be SiO2, and we don't have anything more complicated, so let's just do SiO2. And then comma. Now our list of things that we want to get. So let's go ahead and get the material ID. Oh. I accidentally clicked somewhere else. So material underscore ID. And then comma, and we're going to add another. And so the crystal system is actually a piece of data in the space group field. So it's going to be space group dot crystal system. So right now we're doing the query, but we're not actually storing this. So we should create a variable name to fill this list in. So let's call this entries. So entries equals mpr.query SiO2 material ID space group.crystal system. So now let's just get the crystal systems from this list of entries. So let's create a new variable. Maybe we can call it systems. Is equal. And let's use a list comprehension that you may have seen in the Python primer. So we're going to create a list with an empty brackets. And we're going to put a for loop directly inside the list in a way. So that's what a comprehension is. So we're going to just say entry. And so these are a list, this entries is a list of dictionaries. So we're going to look into the space group.crystal system key. And now I need to add that for loop I was talking about. So entry, space group.crystal system, for entry in entries. And now let's create a count dictionary. So let's call this counts is equal and create an empty dictionary. And let's iterate through this this list of crystal systems and just add an entry into the count dictionary for each crystal system. So for system in systems, if system So if the system is in the count dictionary, we should just add a 1, like add 1 to the value in that count dictionary. If it's not in there, then we should give it a value of 0 and then add 1, right? So if system in count dict, or counts, sorry, counts of system is equal to, we're going to do counts of system is equal to counts of system plus 1, but in Python you can just do plus equals operator. So counts system plus equals 1. So that's just going to add 1 to the value in there. Else counts system equals 1. So I'm going to exit the rise mode real quick so that you can see all of the code at once. It's a little bit smaller, I apologize. Maybe I can zoom in a bit. No, it doesn't like that. Okay. So all we're going to do here now is just plot a histogram. So plot.bar range space group, range of the length of our counts dictionary. So this is going to create a bar, it's going to have that many bars. And then the y values are going to be the counts, so counts dot values. And I'm just going to align it to the center of the page. I think I closed all my parentheses, yep. And then I'm going to make the labels. I used the wrong bracket there, so I need to use parentheses. And then I'm going to just copy this here, range len counts, and just paste it here. And then I'm going to give it a list of the keys. So there's maybe a lot of space groups, but maybe we only want the top 5 or so. So let's do, if there's going to be some space groups, but maybe we don't want the full name because it's going to overlap each other on this plot. So let's just do the first 5 characters of each name. So key 0 to 5 for key in counts.keys. And that's a list comprehension, so I need to put square brackets. And then I'm just going to show this plot. So this should show up with a histogram. So if you didn't totally complete all the plotting code, that's okay, because it's just Python plotting code. But the idea, the main part is in this first part here, where you got the data you're interested in on that query. Okay. So I'm going to resume rise mode so that we can focus on this slide only. So now we're gonna address what Joshua had a question about. If you wanted to do more complicated queries than just a single thing, right? Let's start using some MongoDB operators. So there's operators such as and, or, in, not in, equal to, not equal to, less than, greater than. So these are kinds of things we want. We want to have the database compare something to a value and make a decision about whether to give us that data or not. So we do this with query operators, and they all start with this $sign character. So in MongoDB, these built-in operators start with $sign. So let's learn through an example of how to use these operators. So one of my colleagues, I think last year, brought to attention that there's a lot of interesting research about how some nitride, like lithium nitride, might be a good synthesis. There might be a good synthesis process for lithium nitride by using or synthesis method for ammonia using lithium nitride. So let's go ahead and just get all of the nitrides of alkali metals in the materials project database. So that's what we're going to do in this cell here. So first we need to know what are the alkali metals, maybe. So let's create a list of the alkali metals. I'm just going to call it alkali metals. And so we have lithium. Shout them out. What's another alkali metal? All right. Yep. Yep. Anyone remember the last one? Yeah. All right. So now let's go ahead and figure out what criteria should we be querying on. So I'm going to make a variable called criteria just so it's a little bit cleaner. So criteria equals, and this is going to be a dictionary. It's okay. So it's going to be a dictionary. And so what are we trying to really narrow this down to? We want only things that have both nitrogen and an alkali metal in them. So maybe the elements need to have some criteria enforced on them. So I'm going to do the key elements. And now when you use an operator, instead of putting just a value as the value in this dictionary of query parameters, you're going to put another dictionary. So I'm going to use the curly brackets here. So I created an empty dictionary. So the value of this entry in the dictionary is another dictionary. And this one is going to have a key. And in this case, the key needs to be an operator. So I'm going to use $, and we want it to be in a list of authorized elements of the alkali metals. So there's an operator in for that. So in, and then now the in is the key, and the value is the list that the elements have to be in. So this is going to be alkali metals that we just wrote. I'm hitting A and then tab, and then it popped up as an autocomplete, and I clicked it or hit enter. And now let's go ahead and add another criteria. So at least one of the alkali metals has to be in the formula, in the elements, but it also has to include nitrogen. So they all must include nitrogen. So we have another operator called all. So that's going to be another key. They all have N in it. Actually, I'm not sure it needs to be a list here. Let's try without a list and see what happens. And finally, we want these to be binary compounds. So we don't want everything in the materials project that has an alkali metal and nitrogen and something else. We just want those two. So let's put an enforcement that the number of elements has to be 2. So this is a so it's not in the inner dictionary, this is now in the outer dictionary. So we're adding a key and elements. And 2 is the value for this. So we have, let me put some white space here so that it makes it more clear. We have 2 criteria. Elements, and there's some restrictions on what's allowed in the elements, and then the n elements is 2. And let's get their properties, the materials ID and the pretty formula. So I'm creating another variable, properties, material underscore ID, comma, pretty underscore formula. And so let's go ahead and now see what results we get for this. So we're going to print mpr.query, and then criteria and properties. Oh, I got a REST error. Let's see what it says. All needs an array. Okay, so that's why this needs to be wrapped in an array. So now this is the first 5. So you can see now we have binary nitrides of alkali metals. Are there any questions so far?
Can you use wildcard in combination?
I'm not sure, Patrick, can you? I don't think so.
Wildcard for what?
Like not the ones that not the yeah. Not the materials project wildcards, but Mongo does have wildcards.
It has regex.
Yeah, regex wildcards in it. So if you want to like talk to me after session, I can show you how to do specifically regex stuff. Yeah. Any other questions? Okay. So let's go ahead and do one of these like Mongo wildcard kind of things. Materials project wildcard thing. So you can do it with wildcards. The kind you can either do it using the string query. So it would be like npr.query, and then n-li. So this is in our materials project wildcard syntax that you can do this. So you can get the same thing, similar thing. But this isn't like Mongo wildcards. So if the elements field can't do like the same kind of wildcards. Like we don't have that. That's not built into Mongo. That's built on top of Mongo. So one other thing that we typically do, it's a very common query that you're going to see, is that we only want materials that have a low energy above hull. What that means is they're going to be more stable, more easily synthesized in all likelihood. So this is a very key thing that we usually like filter on in our queries. And so let's use the less than operator on the energy above hull field to do the same query, but only get the values that have low energy. So I'm going to go back to the previous cell here. You can just copy this code and paste if you'd like. I'm just going to do it in here. Actually, no. Let me copy this code, and then I will go to the proper place and paste it. And find all nitrates of alkali metals with low E above hull. So what I'd like you to do is take this code that we copied from the previous part and paste it. Has everybody got this code so far? Anybody that hasn't yet? And I want you to use the less than operator as an additional field or as additional criteria with the E underscore above underscore hull property. So to do that, you're going to add another thing here. So this is going to be another entry in the dictionary, and there's going to be some dictionary in here with an operator that you modify. Any questions I can answer while everyone's working on this?
In the wildcard example you showed just now, can you specify how many elements in there?
See, that's the part that you can't. Actually, there may be a way to do it. It would be kind of complex. I think that you can use like. In that case, we had like we were using like a system. I guess you could do n, and then curly bracket, and then the options. That might allow you to only get. But that would only give you n plus that one element. It wouldn't give you like n lithium 2 or something like that. So whenever you have, my advice normally is whenever you want to do a more complicated query with like restrictions, use like take a little bit of time to create this filter dictionary and then use that. Because it's much easier to figure out what's going wrong because each part is independent. With the single string, it's like kind of harder to figure out what's happening. And it's not as easy to find the source of your problems. Yep.
So how should I apply the less than operator in the criteria statement? Does that go as, I mean, it's a separate criteria.
Yep, so the key is the E above hull. So that's the field we want to apply the less than on. And then the key is going to be $LT for this inner dictionary. And the value is going to be the value it needs to be less than.
Okay. Is that I don't know, is it a string value or is it actual value 10?
It's going to be a, yeah, so this is a good thing. So if you look in the MappyDoc, so let's go ahead and take a look at MappyDoc. E above hull. So if we click the E above hull entry, the calculated energy above the convex hull, and then I guess this is it doesn't say the units. I'm sorry. This should really say the units, and I don't have admin rights on this MappyDoc. But anyway, the units are in electron volts. So 10 MeV would be 0.010 EV. Thank you for that. Maybe I'll submit an issue while everybody is finishing that up. All right, so let's run this and see what we get. All right, so we get lithium 3 nitride, sodium nitride 3, lithium nitrogen 3. So we get a bunch of results. There's 9 out of that big list that we got before that actually have low energy and are probably realizable in an experimental setting. So this is rough. So energy above hull is not. There's not a hard deadline whether you can synthesize something or not. Like a buckyball, for example, we can make those, but they have very high energy above hull. So there's more complicated ways of figuring out whether something can be made or not. We have a paper in Science Advances about that you might want to read. But E above hull is a very good rule of thumb. So treat it like a rule of thumb. Okay. So now with the last 15 minutes of our session, let's do a kind of a small recreation of a paper that we published in like 2 years ago. So when I was an undergraduate working with our group, there was a graduate student who had accidentally found a material with a negative Poisson's ratio. So Poisson's ratio is essentially when you take something stretchy, if you take your, these aren't particularly stretchy, fortunately. Anyway, you take a rubber band and you pull on it. What happens to the cross-section of that rubber band? It gets thinner in its fat side. So when you pull on it, it gets thinner. So that ratio of how thin it gets to how much you've pulled it, that is called the Poisson's ratio. And so oxidic materials, or materials with negative Poisson's ratios, they're very strange. When you pull on them, they get thicker. So they grow when you try to tug on them. So imagine these might be very useful if you are trying to make a scratch-resistant coating. Because if you're trying to compress it, it's going to try to grow against that compression and fill in the crack that you're trying to create when you do a scratch. So these materials are interesting for those applications. And unfortunately, at the time that we were working on this, this was the graduate student who found a negative Poisson's ratio by accident by running the elasticity workflow. There was only one experimentally confirmed oxidic crystalline inorganic material that was known at that time, and it was alpha cristobalite polymorph of silicon dioxide. And this material wasn't that one, and it was it didn't have necessarily a particularly low E above hull, so it wasn't necessarily like we were going to make that one. But it kind of sparked his imagination, like, why don't we try to look for more? And so that's the project I got as an undergrad, is like, why don't you try to find more of these materials? The only catch is that the elasticity workflow is really expensive to run as far as like DFT calculations go. And so try to find them without just doing DFT on everything. So like, let's only do DFT on the most promising candidates. And so what we decided to do, let's use the structure matcher in Pymatgen that you may have seen earlier, but let's totally loosen its parameters it's the cutoffs it uses to check things, so that we were getting like a really bad structure match. So it's going to match things that are like not the same structure, but maybe the structure's going to be similar. So we turn this into like a similar structure matcher.